Hi, this is an overview talk of some work I've been doing on AI and economic growth. Basically, I want to think about what are the implications of artificial intelligence for the past and the future of growth. I'll show you some models and then at the very end talk about some of the catastrophic risks issues. The talk's based on material from several papers of mine. One that I'll spend the most time on actually is the paper with Philippe Aghion and Ben Jones from 2019. Then I have two more recent projects on existential risk. And then I'm working right now with Chris Tonetti on a project that I hope to have a draft of pretty soon. And I'll highlight one or two points from that project. So the earlier paper with Ben and Philippe, there were kind of two main themes that we emphasized there. One is that we want to think of AI as the latest form of an automation process that's been going on for 150, 200 years since the Industrial Revolution. So first automation replaced labor with textile looms and steam engines and electric power and then computers. And in the future, AI may lead to driverless cars. We're seeing that now, and replacing paralegals or pathologists or maybe researchers or maybe everyone. So um, that's kind of the, the first theme. The second theme is that AI may be limited by Baumol's disease, by bottlenecks. And the Baumol sort of idea applied in this context means that growth may be constrained not by what we do well, not by the amazing computers and Moore's law, but rather by things that are essential that labor does, and that at least in the short run, they're hard to improve. So you'll see that that theme showing up throughout my discussion. Obviously, Dorane Somoglu and Pascal Restrepo have written, I feel like, a really important paper every year for the last decade or so. This builds on their work, builds on some important work by David Amu and Morten Olsen, and then a follow-up paper that Ben Jones and Liu put together that I'll talk about in a second as well. Okay, so automation and Baumol's cost disease. Here's the economic environment for the paper with Philippe and Ben. And it's, by now kind of a standard economic environment for these task-based models. So the final good is produced with a continuum of tasks with an elasticity of substitution in this CES setting that's less than one. So tasks are complements, and that's going to build in these Baumol type effects. All tasks can be produced with labor, but once you've automated a task, it can be produced with capital instead. And there's a condition such that if you can produce it with capital, you want to, and we'll assume that condition holds. Basically, the tasks from 0 to beta are the tasks that have been automated. So they're the tasks that are going to be produced with capital. And the tasks from beta to 1 have not yet been automated. So they're the tasks that are produced with labor. And that beta is going to be allowed to change over time. And I'll talk more about that on a later slide. The rest of the model is totally standard neoclassical growth model with a solo type assumption that a constant fraction of GDP gets invested. Okay, so the key allocative decisions to make here, how do you split your capital and your labor into these tasks? But as you can see, everything's perfectly symmetric here. And so you're going to divide your capital evenly among the tasks from 0 to beta. And that means that capital per task is going to be K divided by beta. Similarly, you're going to divide your labor among the tasks from beta to 1. So labor per task is going to be L over 1 minus beta. And so when you oppose that symmetry, you get this sort of reduced form CES production function where you can see the beta and the 1 minus beta each enter twice. And so the first way they enter is the purple beta, this K divided by beta. This is capital per task. And then the green beta is the measure of tasks that capital gets applied to. And similarly, there's an L over 1 minus beta multiplied by the 1 minus beta measure that labor gets applied to. So there are kind of two effects of beta in sort of the green effect and the purple effect. There's the more tasks get to use capital, but there's the, as you apply capital to more tasks, capital per task goes down. Okay. So if you collect these beta terms together, you can write this reduced form CES production function as a conventional CES production function, f of bk comma al, where f is very much the, sigma minus 1 over sigma, power mean. And b equals 1 divided by beta to the 1 over 1 minus sigma power. And notice, since sigma is less than 1, I've written everything so that you could see the exponents are positive. You could see the direct effect. A is similarly 1 over 1 minus beta to the 1 over 1 minus sigma power. That kind of collects the green and the purple betas there into one term. And what's really interesting about that, and this was a point that Philippe and Ben and I made, and kind of the point we're most surprised by early on in that work, is that an increase in beta, if you automate more tasks, that's neither an increase in B or a change in A, but in fact, it's a combination of those two things. So automation with the elasticity of substitution less than 1, that's an important assumption here, an increase in beta simultaneously reduces B and increases A. It's a twist of the technology here. And it's basically, with sigma less than 1, the dilution effects dominate. The dilution effects just get magnified. That's the 1 over 1 minus sigma kind of exponent there. And so, surprisingly, an increase in automation is capital depleting and labor augmenting at the same time. You wouldn't have expected automation to be capital depleting, but that's how it shows up. So that was kind of a really interesting finding from that earlier work. Okay, now let's suppose, just because this is a simple assumption to make, and it leads to some interesting results, let's suppose that a constant fraction of the tasks that we haven't yet automated get automated every period. Right? So imagine we automate 5% of the remaining tasks every period. The tasks that haven't been automated, 5% get automated every period. That's this law of motion here. Obviously, beta is going to converge to 1. It never actually reaches 1, but it gets, arbitrarily close, 99%, 99.9%, et cetera. So beta is approaching 1. Beta is kind of leveling out. What happens to 1 minus beta? Well, of course, 1 minus beta falls to 0. That's completely obvious. But if you look at these equations, you realize something interesting, which is that 1 minus beta falls to 0 at a constant exponential rate. And that rate is theta, right? So if we're automating 5% of our tasks, 1 minus beta falls to 0 at a rate of 5% per year. And that constant exponential decline is going to be very important. Why? Because we'll remember A is 1 over 1 minus beta. So A is going to rise at a constant exponential rate, right? So putting all this together, we've got the f of bk comma al, a standard CES production function that's the reduced form of this task framework, where B is 1 over beta to a power, A is 1 over 1 minus beta to the power. B is converging to 1. That's going to satisfy Yuzawa's theorem. Asymptotically, there's no longer any capital depleting or capital augmenting technological change. B is going to be constant. A is falling to 0. Sorry, 1 minus beta is falling to 0 at a constant exponential rate. So A is rising at a constant exponential rate. And the growth rate of A is theta divided by 1 minus sigma. And that's kind of cool, because this sort of setup with automation, with this twist of the production function, turns out to lead to a kind of a standard setup with asymptotically purely labor augmenting technological change, right? So A is going to grow at a constant rate, B is going to be constant. We're going to get a balanced growth path. And the balanced growth path is going to feature a capital share and a labor share that are interior. You might have guessed, hey, if we're automating 100% of tasks or getting very arbitrarily close to 100%, maybe the capital share is going to go to 100% or 0. No, the capital share and the labor share both remain interior. And if you pick your parameters in just the right way, you could have the capital share leveling off at 1/3 and the labor share leveling off at 2/3. Right? So you get this task model leads to a very conventional neoclassical framework where the labor augmenting technological change is purely driven by the automation process. Okay, so why does this all work? Well, beta is going to 1, so the capital augmenting piece ends eventually. Labor per task is rising exponentially over time as labor gets concentrated on a smaller and smaller set of tasks. Labor per task rises, so effective labor rises, and that's the labor augmenting technological change that leads to growth here. Labor gets 2/3 of GDP. How is that? Labor's, being squished onto a set of tasks that's vanishing. But remember, the elasticity of substitution is less than 1, right? So with elasticity less than 1, the scarce factor gets the returns, right? So labor's the thing that's essential. Capital, yeah, we're great. We've got all these computers that are automating everything away. Computers are cheap. Labor's expensive. Labor gets squished onto this small set of tasks, but those are the tasks that are scarce and essential, so they maintain a high share of GDP. Okay, so this was the Aghion-Jones paper. What are some limitations of this? Well, first, it's only an asymptotic result that occurs as beta goes to 1. So it only occurs, you only get this balanced growth path as 100% or near 100% of tasks are automated. It's not clear that describes the US or other modern economies. So that was something that was a bit of a weakness. This led Ben Jones and Liu in the AER in 2024 to another insight, which is really cool, which is they show how a balanced growth path can occur today with beta less than 1, rather than being an asymptotic result. And the thing they add, which is very, very clever and interesting, is they add better computers. So imagine the production function for tasks is not, imagine there's a Z that multiplies the K, right? So you get better computers over time, you get faster computers, and you have this capital augmenting technological change on the KI, on the I task. They show that the capital share in that case is beta divided by Z, right? And this is a neat result because on the one hand, as you automate more things, that's going to raise the capital share. On the other hand, as computers get better, they get cheaper, and that's going to lower the capital share, right? And it could happen that beta is rising and Z is rising, but they're rising at the same rate, and that leads to a stable capital share, right? And Jones and Liu build a model where that happens. In fact, they make it so that computers have a harder time getting better in just the right way, that beta over Z ends up being constant. And so that's cool. Automation and capital augmenting technological change coexist along a balanced growth path with stable factor shares. Now, notice one other thing. Again, I said beta goes to 1. You might guess, this is not in their paper, but this is kind of, how I'm thinking about it now. You might guess that computers keep getting better, right? So beta goes to 1, computers keep getting better, and so the rise in Z continues. If that happens, the capital share falls to 0. With sigma less than 1, computers are getting cheaper and cheaper and cheaper because of Moore's law, and the cheaper computers dominates the extended use of computers. The price effect dominates the quantity effect because the elasticity is less than 1, and that drives the factor share of capital or computers to 0. Okay? That insight was one of the things that motivated Chris and me to work on our new project. And one of the questions we asked is, well, what's happened to the factor share of GDP paid to computers? And you can look this up in the Bureau of Labor Statistics multi-factor productivity trends if you look at it in the right way. And it's really kind of cool. So I'll show you that in just a second. What do we do with the paper with Chris? We take this basic model that I've shown you so far and we generalize it. And we're asking how much of historical growth in agriculture, motor vehicles, and other key sectors is due to automation? What about software? How much of growth is due to automation? And then we'll use that to speculate on how AI might affect the economy in the future. But as I mentioned, this factor share of payments to computers, here's what it looks like. So in the dot-com boom from the in the 1990s, the factor share paid to computers rose. It got to be above 3% of GDP. But since 2000, the factor share paid to computers has fallen from 3% to just over 2%, right? The price effect is dominating. Computers are getting cheaper, And this is kind of good evidence, I think, that the elasticity of substitution is less than one. Computers getting cheaper is driving the income share paid to computers down. And so this notion that I said before, that as Z continues to rise, the capital share might actually decline to zero, even though labor's getting squished onto a smaller subset of tasks, it does the stuff that's essential. The Baumol effects plus better computers can preserve the labor share, and we see evidence for this in the computer share already in the data. So that's kind of an interesting finding. Okay, you can also, and this is back to the Aghion, Jones, and Jones paper, you can also apply this same concept to the idea production function. So forget automation for goods for a second. Go back to Y equals A times L, where A is the stock of ideas. So ignore the tasks on the goods side and put them on the idea production function side. So imagine new ideas are produced with old ideas and with tasks. And these tasks, again, are complements, and they're initially done with labor, but you automate them over time, which is you start to use more capital, right? Let beta be the fraction of tasks that are automated. You get the same kind of structure that we just explored for the goods production function, where there's a bk, there's f of bk, comma, now I'm calling it c times s because I've used a already for the ideas. S is the number of scientists, the number of researchers, and c is the labor augmenting technological change for researchers. And again, b is 1 over beta, c is 1 over 1 minus beta. And so as you automate more and more tasks, that twists the idea production function and looks like scientists augmenting capital change, technological change. Okay. You can factor out, because there's constant returns of this F, you can factor out the CS, and it's F of BK over CS. And if you look at this for a second, you realize the F part is going to converge to a constant in the long run. And so the idea production function is really just going to depend on C times S in the long run. And then it looks like this, and this is a very familiar thing from a lot of my other growth papers. On the one hand, you've got population growth in the number of scientists, let's say, that's going to help drive growth. But in addition, you've got this factor augmenting piece, this labor augmenting piece from automation, right? And so the asymptotic balanced growth path, the growth rate of the stock of knowledge is the growth rate of researchers divided by 1 minus phi. That's exactly like in lots of my other papers. But now you've got this extra term, which is the scientists get concentrated on fewer and fewer tasks. So scientists per task rises. Okay. In fact, if GS is 0, but beta just continues the way it did before, you automate 5% of the remaining tasks, then even though the number of scientists is constant, scientists per task rises, and that generates the exponential growth in research effort. Okay, so can this lead to faster growth? Well, automation's been going on for decades. This is, again, a theme of that earlier paper. And so GC is going to be theta over 1 minus sigma. If a constant fraction of the remaining tasks get automated each year, that's not necessarily going to raise growth. It might contribute to growth, but it's not going to accelerate growth. However, if AI leads to a faster rate of automation, suppose AI leads theta to rise, that could raise the growth rate. And certainly the things we're seeing from Gemini 2.5 Pro or O3 suggest something like that might be possible, right? Another version is if all tasks were automated. Suppose 100% of tasks are automated. Then all the tasks are produced with capital, and you get this kind of expression. All tasks are done with capital, so that's the K, and then you've got the A to the phi. If phi is positive, then the sum of these exponents is bigger than 1, and not surprisingly, you can get explosive growth. So that's something we talked about in the earlier paper with Ben and Philippe as well. It is possible for growth to accelerate or even growth to explode in these frameworks, depending on conditions. I don't want to claim that's incredibly likely, but it's interesting that it is possible, even in frameworks that I like, where it's kind of hard to raise the growth rate. Okay, this next slide, I want to step back and ask, what would AI accelerating economic growth look like? What would it look like to live in that world? And this is motivated by some things that we're seeing right now in the world. And so here's the story that I like to think about the next 10 years. So in the near term, productivity boosts from AI are already showing up in software, right? Coding, programming is much more productive with AI than without AI. People say there's at least a 25% productivity improvement already, maybe even more. You hear even higher numbers now. And so Dario Amodei, Satya Nadella, Sam Altman, in the next decade, could AI agents automate most coding? In the next decade, this seems eminently plausible. People at the labs are saying not just the next decade, maybe the next year or two, this could happen. And we're already seeing it happen now. Once you automate most coding, you ask the AI, hey, code up an even better AI algorithm. Help us do things, even more productively. Code up better AI agents, agents that can use the computer, and you kind of get this virtuous circle that AI raises productivity at coding. That leads to better coding, that leads to better algorithms, that leads to more productivity improvement and better algorithms. And so maybe we could get really good at writing software, right? Combine that with Moore's law price decreases, lots of these computer chips, and you could ask the AI software agent, to code up virtual research agents, virtual research assistants, right? So right now I go on Zoom and I ask my RA, hey, can you help me with this project? Check my math, maybe make some graphs. Well, it could be that instead of it being a human RA, it could be a virtual RA. And I could be asking this of, Chat GPT o5 instead of my research assistant. And, the virtual research assistant can help me. We can have access to millions of those virtual research assistants. We ask them to help us automate cognitive tasks, right? Do the things that any remote worker over Zoom could do, including inventing new ideas. Not that they necessarily immediately invent new ideas themselves, but could they raise my productivity at inventing new ideas? Sure. And once we automate more and more cognitive tasks, we can tell them to make better algorithms, make better virtual agents, make better computer chips, make better medical technologies, help us design better robots, right? Simulate a world where you figure out how to make the robots work really well. Tell us how to design the robots, tell us how to build the robots. Eventually maybe we have AI and we have robots for physical tasks. And, if the AI is running the robots, what can we not do, right? At some level, it seems like that could automate a lot of things. And so if you follow this chain of reasoning, each step seems not crazy to me. It seems like each step could happen. And it certainly seems like through this story, there's the potential to raise productivity substantially over the next 2 decades. And that would happen by raising growth rates over the next 2 decades. So something like this doesn't seem implausible to me. One thing I'll say, and I guess I end with this on the last slide, ask yourself how much the internet changed the world from 1990 to 2015. And I think the answer is probably a lot. Ask yourself how much AI is going to change the world from 2015 to 2045. I think the answer is probably a lot there as well. Maybe it doesn't all happen immediately. Things take time, but it certainly could happen. So this is kind of the positive case. Let me also give you the negative case, because I think I can kind of see both sides. And the negative case is partly motivated by this graph that I show in every one of my presentations. Growth in GDP per person over the last 150 years looks like a straight line at 2% per year on a log scale, right? So what I like about this graph is that, automation's been going on for 150 years. We had electricity, we had internal combustion engines, we had transistors, semiconductors, lasers, the internet, satellites, smartphones, right? All these amazing technologies, antibiotics, gene sequencing, and yet all of those delivered 2% growth per year, right? So why is that? Well, one hypothesis is that each new general purpose technology, electricity, semiconductors, the internet, information technology, each new general purpose technology gives rise to a whole host of things that diffuse throughout the economy and certainly take longer than we expect. Electricity and computers take 50 years to change the economy, but they do profoundly change the economy. But those new GPTs run into diminishing returns. Once you exhaust the steam engine, you kind of need the next GPT, the next general purpose technology to come out, right? Well, perhaps each sequence of the next great idea is what kept growth rates from slowing, right? If we hadn't had the next great idea, maybe growth rates would have slowed. And from this perspective, maybe AI is the latest great idea that helps us maintain this 2% trend for another 25 or 50 years. This, I think, is the pessimistic view of AI, but it's certainly important to recognize the history of the situation. And lots of other great technologies didn't show up as faster economic growth in the data. So that's two ways of looking at AI. I probably personally find myself drawn more to the optimistic view. And again, that should be surprising given how much I've emphasized this graph in my past research. But it's important to acknowledge both possibilities. Okay, just a few more remarks. This one, the future of the labor market, I don't have great things to say about this. This isn't something I've researched a lot, but I do have a few points that I wanted to make. So first, the world where AI changes everything, the world where we worry AI is going to put a large fraction of people out of work, notice, first of all, that's a world where GDP is incredibly high. If AI automates lots of tasks and we have fast computers and robots doing everything, the size of the pie is enormous. That's not to say the transition couldn't be hard and the political economy could be hard, but there's a lot of resources available there. Second point, as we get richer, we naturally work less. This is the history of the world. There's a nice paper, the last decade by Boppert and Crucell, or Nicola Fuchs-Schundon and Alex Bick and other people. And, hours worked is falling. And that's a good thing, right? We have to get paid to work because work is a bad in most of our economic models, not a good. That's why people have to pay us to do it. And so working less, taking more leisure is a good thing, not a bad thing. On the other hand, I think most of us, certainly economists and researchers, would say there's also good, meaningful work. We enjoy doing our research, and the day that the AI automates me away and I can no longer contribute to the frontier of growth theory, that's going to be a sad day for me. That'll be a difficult day. So how do I think about that? Well, a couple of points. First, notice that my iPhone can beat Magnus Carlsen at chess, and yet chess has never been more popular than it is today. Right? So I do think even if it's feasible to automate all tasks, I think we'll hold back some tasks and say we value them because they're done by a human. We want to watch humans play chess. We want to watch humans run races. We want to watch humans in the arts and in music and in sports. I want to watch Messi play for FC Barcelona. I don't want to watch the robots play for FC Barcelona. So there's this set of tasks that we're going to reserve for people, for experiences, and that'll provide an opportunity for people to work, and that could keep the labor share high, as I've discussed before. The other side to it, though, is I think in some sense, when the pie is really big, maybe a model of the future is like, one long summer camp, right? So I'll probably keep doing growth theory, even though the AI can invent things that far exceed what I can do. I'll enjoy learning from the AI how to think about economic growth, right? So I'll enjoy making pottery, learning to play the guitar, interacting with people, going for hikes, right? I think we'll find meaning one way or the other, but this is a tricky, difficult issue, and certainly there are political economy issues there. Okay, so just a few minutes left. Let me just say a few words about existential risk. So in my reading, and this is very much based on other people's work, there are kind of two versions of existential risk that I find interesting, and this is a nice classification. One is sort of the bad actor class, and the other is the alien intelligence class. So for the bad actor, just imagine ChatGPT-6 as this amazing oracle that's memorized the entire internet and that can interpolate between everything in the internet and even invent new things that are a small step away from what we have, right? If we have this great oracle, a bad actor could ask it to design a COVID virus that's 10 times more lethal and takes 3 weeks for symptoms to be displayed, build it and release it into the world and do serious damage, right? So nuclear weapons were manageable because they were so rare. If every person had a red button they could press and do harm, are we sure that we can prevent all people from pressing the red button? That's a big ask, right? So that's the bad actor class of risks. There's also the alien intelligence one, and this is obviously more speculative, more science fiction-y, but one analogy I like is how would we feel if we found out today that scientists observe there's a spaceship, out there near Jupiter headed toward Earth, right? There's an alien spacecraft on its way to Earth. How do we feel about that? Well, we'd be pretty excited on many dimensions, but probably a part of us would worry, hey, maybe this doesn't end well for us, right? And AI is in some sense an alien intelligence. And what do we think about that? I was on a panel a couple of months ago with a CS professor at Berkeley, Stuart Russell, who's the co-author of, I guess, one of the main textbooks that they use in graduate CS classes on machine learning and AI. And he had a quote that I really like a lot. And that quote is, how do we have power over entities more powerful than us forever? So I'll leave that with you to think about. But if you think about it, it does seem troubling. Okay, so I've written two short papers on existential risk and growth in AI, and they both sort of do these thought experiments that I find helpful. So the first one is kind of based around this Oppenheimer question. And the Oppenheimer question basically says, suppose the best case of AI comes true and AI accelerates growth to 10% per year. So it's this amazing new technology that's going to grow the economy incredibly rapidly if nothing goes wrong. But there's a one-time chance at the beginning that AI kills everyone, right? Do you use it or not, right? What risk are you willing to take? Are you willing to take to get 10% growth a year forever? Are you willing to take a 1% one-time risk of killing everyone? Turns out with log utility, you absolutely are. With log utility, you're willing to take a 33% chance of killing everyone to get that 10% growth. So that taught me I'm not a log utility person. More generally, if risk aversion is bigger than one, so risk aversion is 2 or 3, it turns out, bounded utility, really sharp diminishing returns to consumption, combined with our high living standards, mean you're only willing to take small risks. So with risk aversion of 2, I think it's a number like 2%. With risk aversion of 3, it's a number like 0.5%. And that was very much consistent with how I was thinking about things. But then I realized something else. If AI is impressive enough to generate 10% growth a year, it's probably also going to cure cancer and cure heart disease and lower mortality. Well, what if it does that as well? What if in addition to 10% growth, it cuts mortality rates in half? What risk are you willing to take then? Then it turns out, even with risk aversion of 3 or 4 or 5, you're willing to take huge risks on the order of 25%. Why? Well, now you're comparing lives versus lives. Lives versus consumption runs into the diminishing returns, but lives versus lives doesn't. I just care about not dying, whether it's cancer that kills me or the AI that kills me. And if the AI can cut the mortality rate from cancer, well, I'm willing to take a pretty big risk on that front. And so is everyone else, because we all kind of are the same in this simple thought experiment. And so the surprising thing is maybe because of health improvements, we might be willing to take larger risks. And I think this also tells us, when you're trying to shape AI in certain directions, maybe the health direction, the mortality direction is particularly valuable. Okay, so then that led to this more recent paper that I worked on over the winter, which is, okay, we don't have to take this risk as given. Maybe we're willing to take a high risk, but we'd love to reduce the risk. How much should we be spending to reduce AI's catastrophic risk? And I'd read some things that other people have written about. If you think there, billions and billions and even trillions of future people, and we face this one-time risk today, maybe we should be willing to spend a lot to protect the future generations. So I knew that point. Um, uh, But what occurred to me over the winter is we don't even need to appeal to future generations. from a purely selfish standpoint, we've actually experienced something very much analogous to the existential risk from AI, and that was the COVID pandemic. During the COVID pandemic, each of us faced a mortality risk of around 0.3%, a very small risk, but a non-negligible risk. And we shut down the economies when we faced that risk, right? We effectively spent something like 4% of GDP to mitigate that risk. Well, it seems to me the AI risk is probably at least that large. And so maybe we should be willing to spend something like 4%. Maybe we're massively underinvesting in mitigating that risk. And it turns out if you walk through the value of life kind of calculations, it only reinforces that point. Basically, lives are incredibly valuable. The Department of Transportation, the EPA treat the value of life as $10 million. And so because lives are incredibly valuable, if the mitigation spending is effective, you're willing to spend large amounts, maybe even 5% of GDP for 2 decades, if the mitigation spending is helpful. Just the value of lives is so high, even from a selfish standpoint. Forget future generations, large investments could be worthwhile. You do have to say something about the effectiveness of mitigation. I've kind of put that aside in this discussion, but I'll refer you to the paper. But certainly things like redirecting AI in safer directions, interpretability, all these labs have lots of people who are potentially available to be thinking about safety issues. And so I think the marginal product of some extra funding is probably quite high, and according to these calculations, well worthwhile. Okay, so that's it. So final thoughts. I gave the point about how much is AI going to change the world over the next 30 years. Just because it takes 30 years instead of 5 years doesn't mean the ultimate effects won't be huge. So these points that, oh, we know from economic history that things take time, I think, look at the level effect over the next 20 years. If that's huge, I think that's kind of the main point. And then finally, on this underinvesting and mitigating risks, I do think a policy that's worth considering is taxing GPUs and using the revenue to fund safety research, right? So to the extent that everyone uses NVIDIA computer chips to train our models, and that's mostly true today, maybe less and less true, well, taxing the GPUs, people worry maybe if we slow down China races, but no, if China's using our same GPUs from NVIDIA, tax the GPUs, that slows down research of everyone, and use that revenue to subsidize safety. Something like that seems like a policy worth considering. Okay, so that's it. Let me stop there. Thanks very much, and hope you found it useful. How do I stop the recording here?